Hello everyone, and welcome to this event. My name is Jukka Laitinen, and I'm representing Technology Innovation Institute's Secure Systems Research Center, and I'm acting as a drone software lead engineer and architect in a project called Secure Autonomous Systems. And today's topic is uORB. I'm not going to talk about what uORB is and how it is used, but instead I will tell a story how we get some trouble with it because we are basically using it in a little bit different way, and how we modified it to better suit for our needs. This is the outline of my presentation today. First, I will a little bit talk about our secure autonomous system very shortly, what it is and what kind of domains there are with which we are working on. And then I will dive into the PX4. I gave a presentation a couple of years ago online about PX4 security things. And soon after, I will dive directly into the current uORB implementation and what kind of trouble we had with it. And then I will present our changes to the uORB and finally tell what was the outcome of this project. Okay, so this is our secure autonomous system. We got basically 3 domains, roughly, what we are working on. So we have got the flight and mission operations, which consists of basically web-based ground control station and mission planner, where you can plan missions for individual drones and drone fleets and swarms. And then tooling for over-the-air upgrades to the drones and collecting telemetry data and analyzing the data and such things. Then the drones itself, which have this quite typical architecture. So we have got the real-time flight controller and then companion computer connected together via Ethernet, basically. Over micro XRC DDS, so we are running ROS on the companion computer. On this slide, it's called mission computer. We call it mission computer. And then we have got this secure wireless mesh that we use to connect our drones together. So the drones are actually communicating with each other and also to the ground station. So that secure communications is one area. And we selected very early in this project PX4 as our real-time flight controller because of its modular design and this great community that we have here, and also permissive license, and there were many good things about PX4. So we have been mainly working with PX4. This picture is from my earlier presentation a couple of years ago. I'm not going through now all the things what I presented back then. We have been working with many security things inside PX4, and many of those things are sort of easy to solve or require some basic engineering. Like when you are making a product, you can always close some extra debug interfaces from your product, and you can store data in encrypted format instead of unencrypted plain text on your memory cards. And we actually implemented even some interfaces and upstreamed those to the PX4 for the purpose back then. One big thing for software security is always the memory protection. We always try to have hardware-enforced memory protection in all the software, which is this kind of traditional software architecture which doesn't have, which is not like formally modeled and formally verified. But we enabled in our flight controllers, the embedded flight controllers, we first enabled this NATEX protected build mode, which basically enables a simple form of memory protection. So it splits the memory space in half into user space and kernel space. And basically the idea is that whatever runs in the user space cannot access directly the kernel space memory. But whatever runs in the kernel down there, that then can access all the memory. And by that we could, for example, isolate some communication protocols such as Mavlink from some security critical things like cryptography, which we place in the kernel side. This works, and there are examples even upstream to the PX4. So it runs on STMs and also our own flight controller hardwares. But there has been some issues with that, which I'm going to talk next. So we are not running this flat embedded firmware like memory models where everything is open, but instead we try to enforce the hardware enforced memory protection. So we have been flying this NATEX protected build with PX4, and then we started looking into how we could run PX4 in this full process model so that every PX4 module would be running as an isolated process and not having access to other modules' memory directly. And we have our own flight controller hardware based on a microcontroller that has an MMU, so it's an application-grade microcontroller. We are using Microchip's PolarFire SoC. It's a quad-core RISC-V microcontroller, and we have built several variants of the flight controller out of that. But running PX4 in this process model, it has some challenges, of course, because probably nobody has tried that before, and that kind of model in embedded world is quite, it's not so common. And I have listed some of the issues here, but one of the big things is the uORB, and well, even though I promised that I won't talk about what it is, but it's the common publish-subscribe interface, which is used by basically every module and driver to pass data to each other. So a data creator can advertise and publish data to a named topic instance, and then another module can subscribe to the data by knowing its name and instance number. So that's the basic idea. But it doesn't work in their process. And when we have been running the protected implementation, for that we did some additions to the uORB, also to the upstream, so we made it work. But there are some performance issues, first of all, because when we have a subscriber in the user side of the memory, it cannot access any data produced by a publisher in the kernel side. And because of this, there is a system call interface that every time a subscriber accesses the data, it goes through the system call interface down to the kernel and fetches the data and comes back. And now if we put some high-frequency publishers and subscribers into the user space, it creates a huge amount of these system calls, and it gets really heavy. Even though one system call is not that heavy, at least not on ARM, but when you do tons of them, it really starts to be a pain. And for security reasons, we actually would like to minimize the kernel. So to make it more performant, you can obviously put all those high-frequency publishers and subscribers into the kernel side. Then they don't need to go through this system call interface. But then your kernel is bloated and big, and that's not a really secure way to do it. Then compatibility or test coverage issues. In the protected build mode, the way how the data is accessed is different when you do it from the user side to the kernel than it is in the normal flat build. And it's also different what it is in the PX4, in the Linux build, the software in the loop build, for example. So that's also not so nice thing that we have. And the big thing for us is that it doesn't work inter-process at all. So if you launch different modules in PX4 as separate process, memory protected processes, they cannot just communicate with current uORB. And I've got a picture here that illustrates the problem. So basically, if you have got two processes here, or two PX4 modules, one which I call here sensors, another one which I call controller. They are imaginary processes, but well, actually there is a module called sensors, of course, in PX4. But now sensors process is actually producing and publishing data in those uORB device nodes, which have a memory allocated in the context of the sensors process's own memory space. Now, when the controller process gets scheduled into execution, the memory mappings change, and nothing which was in the sensors processes memory is no longer visible to anybody. Not even if the controller process would go through the kernel, because it's not visible to the kernel either. So it's the basic MMU mapping of the processes. And also the other way around. So if this controller process would like to have a callback from the publisher, so it registers a callback to the publisher that call this function of mine when there is new data. Obviously, when the sensors module is running, it cannot just call a function which is in another process's memory space, because it cannot access that. They are protected from each other. So we started thinking that we probably need to replace the whole uORB with something that can actually work inter-process, and collected some requirements for that. So obviously, working inter-process is the must thing for us. We want it to work like that. It should work in both NATEX and Linux, because we are running PX4 in both of those environments. And it should also work in all NATEX build modes, because we're actually using all of those in our different software configurations. And it has to use the current uORB interfaces, because we don't want to go to modify every PX4 module just to get our own messaging in place. That would be insane. We want to use PX4 as is, because it's great as it is. And also, it has to be performant enough so that we can still run the same code base on the existing off-the-shelf flight controllers, like those Holy Bros STM32F7 controllers or others. So it has to be performant and low memory footprint. But we don't actually require anything extra, what is not yet there in uORB. So we are not talking via uORB from one drone to another, so we don't need distributed messaging. We don't need any extra quality of service things. So uORB works with best effort, basically, and you just design your scheduling and queue lengths in a way that you don't lose data if you cannot afford losing data. We don't need persistent storage for undelivered messages, and namespace support here is a little bit confusing. It's jumping ahead of this presentation maybe, but what it means that we don't need to run several PX4 instances on the same PC or same machine. And that's because we are always running PX4 in Linux inside a Docker container. So we are always Dockerizing the PX4 and then putting the Docker into the cloud or on some PC or somewhere else. So what we then ended up doing, we changed the design a little bit. So we wanted to keep the original concept. We still want the subscriber to be able to directly copy the data from the publisher's memory, but we changed it in a way that we just allocate the memory in a way that it's accessible by both publisher and subscriber, even inter-process. And for this, we decided to use POSIX shared memory, which is a standard interface. And when using that, we can also remove the current CDEV interface altogether. Then we implemented our own polling interface, so when a subscriber wants to wait for new data, it can poll on some uORB, but there is no poll for POSIX shared memory object, so we created poll interface inside the uORB library itself. And then we implemented inter-process uORB callbacks. I will describe those a little bit later, very shortly. And we wanted to keep the functionality the same, so we tested the new uORB implementation against the existing one running on STMs, on Linux simulator, and of course with those tests framework that is in PX4. And as I said earlier, we kept the original interfaces to avoid any changes to other parts of the PX4. This now shows how it now works. So basically when sensors publishes some data, it creates its topic instance. So it first creates a shared memory, POSIX shared memory segment, then it allocates the uORB object inside that. And now when the other process who subscribes to it needs the same data, it can map that same shared memory segment to its own memory space. So now those both can access the same device node, but still the other memory is protected. So only those things are shared which needs to be shared across these processes. And about those callbacks, so when a subscriber registers a callback to the publisher, it actually also creates an own callback thread to its own context. And the callback thread goes to sleep in a semaphore, and we allocate that semaphore also in the shared memory. So now when the publisher runs, it can kick that semaphore, and then the subscriber can run the callback in its own context entirely. Now here is a boring picture, all black and white and lots of boxes. To point out there, up there are the interfaces, C interface, C++ interface. C interface is a little bit modified. C++ interface we didn't change at all. It's exactly the same as before. uORB system command is exactly the same as before. Then there is one centralized broker object called uORB manager. It's basically the same manager that is there, but now we allocate that inside one shared memory object. So that is an object that any process can map to its memory space to get access to the uORB. Another thing that, and then when a publisher wants to publish data, it maps the uORB manager to itself, and then it creates the device node which it wants to publish. And then subscriber can map those same objects to its space. Now I'm not going to go through these other details here. This is background information. This is only if you don't know the POSIX shared memory, how it works. I will just quickly go it through. So this interface is only used inside our uORB library. It's not visible to anywhere outside. But how a typical publisher then actually creates the shared memory object is that it opens a named shared memory object the same way as it would open a file. It sets the size for it, and then it calls mmap to map it into its own memory space, getting a direct pointer to the shared memory. And typically, actually, after this, you also close the object because you don't need the file handle anymore. When you get the pointer, you have a reference to it, and it's not going anywhere, so you will use the memory directly. And the subscriber would do the same, then just open the named object and map it to its own memory, and typically also close it. And nice thing about the POSIX shared memory interface is that it works the same in all NATEX build modes. From the user point of view, it seems that it works the same. Obviously, in NATEX flat and protected build modes, it doesn't really map anything, but it allocates the memory and returns the pointer, and seemingly works the same as with real MMU. And in Linux and NATEX kernel builds, there is a real MMU mapping of the memory, so it works as specified in the POSIX spec. And those new interfaces that we are using in our uORB implementation, they are supported in NATEX upstream from version 12.1 onwards. We have actually made those interfaces into NATEX, so we have also backports on older versions of NATEX, because we started it on older versions, but this is the upstream version where they actually are available. This is a recap of what kind of changes we did to the original C interface. These ones are not so much used in PX4 code base nowadays, so there are very little changes needed to the other PX4 parts because of this. But basically we changed those advertiser handle type and and because we changed the advertiser handle type to a structure, we also changed the publish to pass a pointer to the structure instead of the whole structure. But that's sort of a minor detail. And then we added a new type called uORB sub T. Previously, a subscription handle was just a file descriptor. So uORBs were accessed by opening a device node, opening a file and getting a file descriptor integer. But we needed that to be something else as well. So we changed that type as well, and then we checking of validity of those handles, we added a couple of wrappers for them because previously the code is filled with if advertiser handle is null or if subscription handle is greater than -1. So it's nicer to just have those wrapper functions to check the validity. And as I mentioned, we created the polling functionality inside the Muir library as well, so that the subscriber can wait for data to be published into a topic. Now I will just jump into what was the outcome of this. So first I will show some performance figures. We measured performance on some Pixhawk 5X. I'm not presenting performance figures now on our RISC-V because they are similar, but since it's not commonly available, so this is maybe nicer. In the normal PX4 flat build, what typically, this is the normal stuff that you have. It runs a little bit faster with this new model. There is a difference of 3 percentage points with certain configuration on this hardware. And with protected build, there is a huge difference, and this really depends on what is your allocation between those memory protection areas. So how many components you put into the user space and how many you put into the kernel space. So if you put lots of high frequency publishers or subscribers into the user space, then the saving is even bigger. So this CPU load doesn't really change so much anymore at all with this new, because everybody is accessing the Muir data directly instead of going through this system call interface in protected mode. With the flash memory, it consumes a tiny bit more flash. That's because there is some new code added to the NATEX kernel, so basically the increase comes from there. And also SRAM consumption grows a bit because the NATEX is keeping track of those memory mappings so that you can map and unmap those memory areas. But those are actually, for us, those are insignificant numbers, what we have. So what we got was that as I said, we got improved performance in all build modes, and the big thing that we got was that now we can actually run this inter-process. So we have actually had prototypes where we fly drones with every PX4 module running as a separate process, isolated from each other, and that's really where we were aiming for. And now all the code parts are the same in the simulator and in the embedded FMU because they are all using exactly the same interfaces, this POSIX shared memory interface and shared semaphores and so on. Now, some drawbacks, which are not really, these are not drawbacks for us currently because we are not needing these things, but this relies on POSIX shared memory support being in the operating system. So it's now only available on fully POSIX compliant operating systems such as NATEX and Linux. So if we would need to ever run PX4 on some other operating systems such as probably GURT or FreeRTOS, which might happen, then we would need to add some wrapping code to implement these interfaces. It won't be so much work probably, so we are not so worried about that. And then the other thing that I mentioned that we don't currently support in our code base running several PX4 instances running on the same machine, because we are running each PX4 inside a container in Linux environment. So from the PX4 point of view, it is in its own environment already inside the container. And then the negligible memory consumption. And I reserved some 5 minutes for the questions, because this was quite a fast run through with touching operating system internals and memory management and what not. So there might be questions, and if it's too difficult to ask questions now, so please come to ask anything afterwards. So thank you. Yes.
Did you check where the RAM increase comes from?
Sorry, did I check that RAM?
RAM increase, where does it come from?
Yeah, RAM increase mostly comes from the operating system side, so it comes from the NATEX. NATEX, when you do memory mapping, the NATEX keeps a track of all the memory mappings, so basically it adds all the mappings to a list, and then so that you can also unmap it, so the NATEX can find it. And it's actually doing that same thing also in flat mode when there is no real memory mapping, but of course in the real kernel build it really needs to do that for each process, so it mostly comes from there. There are some things that we had to allocate some structures inside uORB statically, because when you are putting something inside a shared memory object, you have to know the size of the object in advance. So there are some structures that we have to allocate space for, some things that you probably never need. But yeah, mostly from NATEX side. Yes?
I'm not sure if I understood how the performance was measured.
Yeah.
A unit was in percent, so is this system load?
Yeah, sorry. I can. So the CPU load was measured by running the flight controller as idle. So it's mostly running all the high frequency stuff like EKFs and other things, and just running the PX4 stop command and checking the CPU load number from the PX4 top command from the PX4 shell. And then the memory figures were gotten from proc file system. So NATEX provides the proc file system, and then there is the memory.
So do you also have any estimates for how it affects latency or the throughput?
It doesn't really affect latency and throughput by design, because also the original uORB directly just copies the data from subscriber, from the publisher's buffers. So it's just accessing the data in the same way. There isn't really much difference in the way how it actually operates. It's only the difference where the data is allocated in the memory and how it's managed, so to say. But it's a good point that maybe using perf would also give some information. Obviously, there is some difference in, for example, in the polling interface, because it's written, and then maybe also in callbacks. In callbacks, there is a latency difference in case you are running it in these memory protected modes. Basically protected mode. In kernel mode, there is no difference, because you cannot run the kernel mode at all without this change. So, yeah, good questions. Thanks. Anything else? Maybe I should mention that we haven't offered any of this into upstream except for the NATEX parts, which are those standard POSIX interfaces. It's just currently just in our own repositories. We have been flying with this uORB implementation for half a year now, approximately. So. Yes?
So will you
No, it's not closed. It's open. But now here's the thing. In our main line, there are tons of other stuff as well. And those branches where we developed it, they are a little bit outdated. And also we are using actually the latest NATEX in our main line because that's required by our own hardware. Our own hardware support is only in the latest NATEX. So I'm open to making some kind of branch where it's nicely available if there is interest. So please contact me. But then we need to just decide on which NATEX version and on how do we want to do it. Okay, I guess time is up. Thank you, and please don't hesitate to ask more.